Hi everybody, this is the second video in the waves topic on Physics A-Level. This will look at wave properties, looking at exam questions. In this video we're going to have a quick recap of some of the key ideas from last lesson, and then we're going to look at some exam questions at grade A and above standard. So quick review, pause the video and just check that you're confident with the definitions and the meanings of each of these terms. As we said last lesson, you need to know all these definitions. So pretty much word perfect. There might be a slight variation, but frequency, wavelength, time period, amplitude, transverse waves, longitudinal waves, progressive waves, in phase, anti-phase, and this idea of wave fronts. So if you're still not confident with these, or you've forgotten them, do have a read through, do write them out, prioritize not just the learning of them, but also the understanding of the significance of each of these terms. Okay, exam questions. So have a read through these two questions, pause the video and see if you can answer them, and then we'll go through the solutions. It is a little bit difficult to find A-star questions, certainly, but even grade A questions when we've just covered such a small amount. So what we looked at in the previous video was pretty much GCSE level, maybe a little bit beyond. So these are two typical exam questions. Whether they're grade A or A-star, possibly not, but they're really, really important to understand these. So pause the video and have a go at each of these two questions. Right, here we go. Question 1. It says we have a frequency of 3.5 Hertz. We've got this representation using wavefronts that we talked about in the first video. And it says calculate or determine the wavelength of the wave. So all we need to do is to look at two consecutive wavefronts. We go from 2 centimeters to 5 centimeters. The difference between the two is 3 centimeters, or in meters is 0.03. Part B, calculate the time it takes for a crest to travel a distance of 12.5 centimeters. Right, well, we've worked out the wavelength and they've given us the frequency. So if you're ever struggling with a question, I suppose one approach is just to calculate something. What can you calculate? They've given us the frequency, they've asked us to find the wavelength, so we can find the velocity. So V or C is equal to F times lambda, and we can work out the velocity. If we know the velocity and we're given a distance, then we can use V equals S over T to make T the subject. So the distance or displacements travelled divided by the velocity will give you the time. So always have a go, certainly. Always show you're working out. Also, if you couldn't answer part A, if you just couldn't understand what was going on here, but you knew that you needed the wavelength, and that's kind of implicit in the question, very often, not always, but very often part A will say calculate a thing, and then you'll need that for part B. So if you weren't sure how to interpret this diagram, make up a wavelength. You can do that. Just say, assuming the wavelength is 2 meters or 5 centimeters, then you should, hopefully, if you show all you're working out, get 3 marks, even though you couldn't do part A. So that's another exam tip. Always have a go and make up values. You may not get full marks, but you may well. So a good examiner should give you full marks for that. Right, part C. So we can see that A and B, it appears judged by eye, that they're in the same position in their cycle, and also particle D or point D is in a similar position. So we could say, judged by eye, approximately, A, B and D are all in the same phase because they're at the same point in their wave cycle. Remember that the wavefront, we could assume this is the start of the wave. So this wavefront over here, that's the start of the next wave. So A, B and D are all in the same phase. So C is not in phase. Be careful. If you write it's antiphase, that's not strictly true. In fact, it's not true. Antiphase has got a very particular meaning. That's 180 degrees out of phase. So if position C was right in the middle, or slightly to the right of the middle, then we might assume that it's antiphase. But all we can say with confidence here is that it's not in phase. We could estimate what the phase difference is, but it's probably safer just to say it's not in phase. Okay, question 2. At first glance, this looks relatively straightforward, but it's actually quite complex. This is testing your understanding of waves and representing waves and comparing two waves that are not in phase. So This could be a grade A question, potentially. It's certainly important that you understand very, very clearly how to represent waves and all those terms we've talked about before, for example, phase and weight and so on. So let's have a look. We've got a progressive wave. These lines shown are 0.06, so 6 centimeters. And we have two photos taken at different times. Right, there's a typo here. That's a bit confusing. That should be seconds, not meters. So the time is 0.015 seconds, not meters. Hopefully you coped with that typo. And both waves are moving to the right of the page. So the wavelength, right, how can we work out the wavelength? So we need to work out that, well, this is a distance shown here on the right, not time. And we can count 1, 2, 3, 4, 5, 6, 7, 8 of these spaces. Takes us back to the start point, back to the peak. So 8 multiplied by 0.06 would be the wavelength, and we can calculate that as 0.48. Right, the frequency. I think a common mistake here would be just to find maybe 1 over t, which is not going to be correct because that time there doesn't represent a full wave. So we need to be aware that we had 8 spaces to represent a full wave, and the time between these spaces is 0.015 seconds because that's the difference between each of these waves here. So we have 8 lots of 0.15 seconds. So multiply that by 8 will give you 1.2 seconds. And then we can calculate the frequency. It's the reciprocal of time. So 1 over 1.2 is 0.83 Hertz. Okay, I think A and B are potentially complex, but once we've got the wavelength and the frequency, then we can find the speed. So V or C is equal to your frequency multiplied by your wavelength. As we mentioned before, if you could not do part A or part B, then if you just write, assuming that the wavelength is and the frequency is, you should, if you show your full working out, get the full marks. Now, it depends on the examiner, but it's worth a go, certainly. And for 1 mark, I'd like to think that an examiner would give you that mark. Part D, compare the amplitude of the wave at A and B. A really common mistake here would be to say that A is maximum and B is 0. But we have to understand the definition of amplitude. So amplitude is the maximum displacement from the fixed position. Remember that this is just a static photo, but if this was moving, then let's look at position A first of all. Then it would be going from maximum, as shown, down to 0, down to minimum, back to 0, back to maximum, as it moved through the wave cycle. Similarly for B, at the moment it's at 0 displacement, but a short time later that will go up to maximum, then back down to 0, then minimum, back down to 0. They both have the same amplitude. At this particular point, they have different displacements, but their maximum amplitude, as they both oscillate about the fixed position, will be the same. So they have the same amplitude. That's a really important idea. And it's fixed for a progressive wave. That's a general principle. As we'll see later on when we look at standing waves, stationary waves, the amplitude is not fixed as we move along the wave. So that's a different presentation. And the displacement varies between maximum and minimum, but the amplitude is fixed. So I think the exam tip here is to practice lots and lots of questions. That's good practice anyway. But I think in particular, with this idea of waves, you've got to be really confident in whatever way they are represented, whatever context you're given, you feel confident that you can apply your understanding to that question. Okay, good. So these are both fairly standard questions. Whether they're grade A or A star is debatable, but they're certainly very, very important. As we progress through the waves topic and we introduce some more complex ideas, then they will lend themselves certainly to the grade A and A star level in the exam.